Hello everyone, my name's Iman. Welcome back to my YouTube channel. In today's lesson, we're going to connect thermochemistry with electrochemistry by looking at how the movement of electrons is tied to Gibbs free energy and spontaneity. We're going to compare cell potential with free energy, interpret what a positive or negative voltage means, and then use these ideas to relate E cell to the equilibrium constant. And by the end of this lesson, you should see that electrochemistry is really just thermodynamics measured through a voltmeter. So let's start with the big idea. If a reaction pushes electrons forward on its own, meaning it has a positive cell potential, then it is capable of doing work. When a reaction can do work, its Gibbs free energy change is negative, which means the products are favored and the equilibrium constant is greater than 1. On the other hand, if a reaction needs a push, meaning the cell potential is negative, then the free energy change is positive and the reactants are favored, so the equilibrium constant is less than 1. These are all different ways of describing the same thermodynamic truth. Systems move spontaneously in the direction that lowers their free energy. All of this is summarized mathematically through 3 key relationships. The first is delta G naught equals negative N times F times E naught. This tells us that the standard free energy change is directly related to the cell potential, where N is the number of moles of electrons transferred in the balanced redox reaction, and F is Faraday's constant. The second relationship is delta G naught equals negative RT times the natural log of K, which links free energy to the equilibrium constant. And because these 2 equations both describe delta G naught, we can combine them to arrive at E naught equals RT divided by NF times the natural log of K. This lets us go back and forth between voltage, free energy, and equilibrium. It is also very important to emphasize that the value of N must come from the fully balanced redox reaction. It is not pulled from the half reaction separately, but from the final electron count once the electrons cancel. Now, based on these relationships, we can make 3 quick interpretations. If the cell potential is greater than 0, then delta G naught is less than 0, and K is greater than 1, which means the reaction is spontaneous as it's written. If the cell potential is equal to 0, then delta G naught is equal to 0 and K is equal to 1, which means the system is at equilibrium. And if the cell potential is less than 0, then delta G naught is greater than 0 and K is less than 1, meaning the reaction is non-spontaneous as written. Let's look at a quick example to apply this. Suppose we have an electrochemical cell with a standard cell potential of positive 1.2 volts, and the reaction, it transfers 6 electrons. The question is, what is the free energy change? To answer this, we would substitute those given values into delta G naught equals negative NF times E naught. So that becomes negative 6 times Faraday's constant times 1.2 volts. When you calculate this, you get negative 694,692 joules per mole, which is a large negative value. This confirms that the reaction is spontaneous. Now let's solve that second problem together, step by step. We're given an equilibrium constant of 3.1 times 10 to the 9th for the reaction, where solid copper plus 2 silver ions form copper 2 plus and 2 atoms of solid silver. Part A asks for the standard Gibbs free energy change at 300 Kelvin. So here we're going to use the relationship delta G naught equals negative RT times the natural log of K. Here R is 8.314 joules per mole per Kelvin, T is 300 Kelvin, and K is 3.1 times 10 to the 9th. When we plug everything in and we calculate, we're going to get that delta G naught is negative 54,500 joules per mole, or negative 54.5 kilojoules per mole. So that answers part A. Part B asks whether the reaction is spontaneous as it's written. Because the standard free energy change is negative, the reaction is spontaneous under standard conditions in the forward direction. Finally, part C asks which species are favored. A very large equilibrium constant means that products dominate at equilibrium. So in this reaction, the products are copper 2 plus in solution and solid silver. So relative to the reactants, copper 2 plus and solid silver, the products are favored. Now let's shift our topic of interest a little bit and talk about metal activity. When we talk about how active a metal is, what we're really describing is how willing that metal is to lose electrons. A metal that gives up electrons easily is a strong reducing agent because it reduces something else by donating its own electrons. A metal that holds onto its electrons tightly is a weak reducing agent. One of the simplest ways to observe this difference is by watching how metals react with water. When a metal reacts with water, hydrogen ions from water get reduced to hydrogen gas, and the metal itself becomes oxidized. That means only metals that are very eager to give up electrons will react with plain water. The most active metals, like sodium and potassium in group 1, they are so strongly reducing that they can react even with cold water. Slightly less active metals like magnesium or calcium in group 2, they still lose electrons readily, but not quite enough to react with cold water. They need additional energy in the form of hot water or steam. Transition metals generally don't react with water at all, but they can still react in acid where hydrogen ions are present in a more easily reducible form. And finally, at the bottom of the activity scale, we have the coinage metals, copper, silver, platinum, and gold, which are so reluctant to give up electrons that they typically do not react in water or weak acids. So as we move from group 1 to group 2 to transition metals and then to coinage metals, we're really moving from metals that are easily oxidized to metals that are very difficult to oxidize. This reactivity trend is the foundation for displacement reactions. So if you place a solid metal into a solution containing ions of another metal, the more active metal will give electrons to the less active one. So in other words, the stronger reducing agent will be oxidized and the weaker reducing agent will be reduced. A general way to write this is metal 1 plus metal 2 cation makes metal 2 plus metal 1 cation. But this only happens if metal 1 is higher on the activity series than metal 2. Now, let's apply this to a quick concept check. The first question asks which statement about metal reactivity is true. Let's read each answer choice and work through it. A says nickel metal is an unreactive metal. This one is not true. B says copper metal reacts only in acidic water. Copper does not react in acidic water. Most of the time, it does not react with water at all. So option B is not correct either. C says magnesium displaces copper in a reaction with copper 2 nitrate. This is true. Magnesium is more active than copper, so it can displace copper from a compound containing copper ions. This actually makes option C the correct answer, but we're still going to work through D. D says tin displaces magnesium in a reaction with magnesium nitrate. Tin cannot displace magnesium because tin is less active than magnesium. So this statement is false. Again, the only true statement is C, so the correct answer is option C. For the second question, what is the product when iron is added to copper 2 nitrate? Iron is above copper in the activity series, which means it is more easily oxidized. Iron will lose electrons and become iron 2 ions in solution, while copper 2 ions will gain those electrons and become copper metal. So the products are iron 2 nitrate in solution and solid copper forming on the metal surface. So with that, we've been able to answer both of these questions, and we are ready to move into our next topic. So now that we've really built up an understanding of how metals differ in their tendency to give up electrons, we can see how this idea is then engineered into real devices, into things like batteries. A battery is simply a controlled redox reaction that has been packaged so that the electron flow can be routed through a circuit and turned into usable work. The challenge is that good battery design has to balance several competing goals at the same time. We want something that's small and lightweight, but we also want it to last a long time. We want high power output, but we also want thermal stability. And ideally, we want it to be reversible and safe for repeated use. These are not easy design constraints to satisfy simultaneously, which is why battery chemistry is such an active engineering field. The first big distinction we want to make here is between primary and secondary batteries. A primary battery is a single-use battery. Once the chemical reaction reaches completion, it cannot be reversed, so the battery is discarded. Alkaline batteries and a lot of zinc air or zinc mercury cells, they fall into this category. In contrast, a secondary battery is designed so that the redox reaction can be reversed when an external voltage is applied. So this allows it to be recharged and reused many times. Rechargeability requires extra engineering because recharging can produce gases or it can cause material movement inside the cell. So secondary batteries are really built to minimize gas formation and keep the reacting materials physically contained and chemically stable during cycling. Different battery chemistries are then chosen depending on the needs of the device. Zinc air and zinc mercury batteries, they're primary batteries. They are very lightweight and they have a long shelf life, which is why they are widely used in hearing aids. Lithium ion batteries, these are secondary batteries, and they dominate portable electronics and electric vehicles because they have extremely high energy density, meaning a large amount of chemical potential energy stored per unit mass. Lead acid batteries are also secondary batteries. They are much heavier, but they can deliver very large surges of current, which makes them ideal for starting car engines. Nickel cadmium and nickel metal hydride batteries, they are also secondary batteries, and they are common in household rechargeable devices. Now, lithium ion batteries, they deserve a little bit of special attention because they represent the most advanced balance of cost, energy density, and rechargeability that's available today. In a lithium ion cell, lithium ions move through the electrolyte while electrons flow through the external circuit. During discharge, lithium leaves the anode and it's inserted into the structure of the cathode. Then during charging, an external voltage drives the ions back in the opposite direction, which helps restore the original chemical state. Lithium works so well because it's extremely light and it can move rapidly through solid structures. And this gives lithium ion batteries both high energy density and high efficiency. But the same property that makes them powerful also introduces risk. Storing so much energy in such a small mass means there's very little margin for error. If heat builds up faster than it can be dissipated, the internal temperature can then rise pretty quickly, and that can initiate a chain reaction called thermal runaway. This is why lithium-ion batteries require careful design of separators, casing materials, and even heat management systems. And it is also why they are not permitted as commercial cargo on airplanes. With that being said, there are a few general engineering principles that apply across modern battery systems. Most batteries today use solids or pastes rather than liquid electrolytes to prevent the loss of reactive materials and also to improve safety during recharging. Any inefficiency in the electrochemical process, that shows up as heat instead of work. So controlling heat dissipation is really essential for both efficiency as well as safety. And because mass matters, especially in portable electronics and in electric vehicles, modern batteries rely on low density, high charge density materials, which is the central reason that lithium-based designs have become the dominant technology. Let's pause here and check our understanding with a couple of questions. The first one asks, which type of widely used battery is not rechargeable? We have A says nickel cadmium, B says lead acid, C says lithium ion, D says alkaline. We just discussed that primary batteries are single use, while secondary batteries are rechargeable. Nickel cadmium, lead acid, and lithium ion are all secondary systems, which means they're designed to be recharged. The only primary system in this list is the alkaline battery, so the correct answer is D. The second question says, which of the following is true regarding the engineering of modern batteries? A says batteries are made from liquids and gases because it is more affordable. We just established that modern batteries rely on solids and pastes specifically to avoid loss of material and to improve containment. So A is not a true statement. B says primary batteries are preferred over secondary batteries in all cases. This is also not correct because the right choice really depends on the application. C says that it is important to control heat dissipation to improve efficiency and prevent fires. This matches exactly what we just discussed, especially for lithium-ion technology. In fact, this is our correct answer. D says, we're still going to read D, it suggests that efficient batteries use very dense materials to reduce transport weight, which is the opposite of what is true. Lighter, low density materials like lithium are in fact preferred. So the correct answer here is option C, because stability and safety are directly tied to how effectively heat is managed inside the battery. Now let's shift from electrochemical devices back to a real-world consequence of oxidation, and that is rust. Rusting is simply the slow oxidation of iron in the presence of both water and oxygen. Over time, iron atoms lose electrons to oxygen, and they form hydrated iron oxides, which we recognize as rust. We can express it as iron plus water plus oxygen forms iron 2 hydroxide and iron 3 hydroxide over time. This reaction is thermodynamically favored because iron is more willing to oxidize than oxygen is to reduce. And because once rust forms, it does not create a protective barrier. Instead, it's going to flake off, it's going to expose fresh metal, and it's going to allow the process to continue. This is why rust spreads rather than stops at the surface. Now, there are several practical ways to prevent rusting, and all of them rely on the same underlying idea. Protect the iron by making sure another material is oxidized first. So, galvanization, it coats the steel with zinc, which is a more active metal, and it's going to oxidize preferentially. Sacrificial electrodes, they use magnesium or aluminum for the same reason. Those are more active metals that sacrifice themselves so that the iron beneath is preserved. Stainless steel works by alloying chromium and vanadium into the iron. These elements form a thin, adherent oxide layer that seals the surface and stops further oxidation. And finally, physical barriers like paint, wax, or polymer coatings also prevent water and oxygen from reaching the metal at all. With that, we're going to transition into our last topic for this unit, and that topic is atom economy. This is an entirely different topic, but it's still rooted in sustainability and in efficient chemical design. Atom economy is one of the 12 principles of green chemistry. The core idea is that a good synthetic process should incorporate as many of the atoms from the reactants as possible into the final desired product, rather than letting any of those atoms leave as waste. In other words, a reaction with a high atom economy turns most of what you start with into what you want. A low atom economy means a lot of your starting material ends up as byproduct rather than product. The formula for atom economy is the molecular weight of the product atoms utilized divided by the molecular weight of all reactants multiplied by 100%. When you apply this equation, stoichiometry has to be taken into account. You don't just sum atomic masses, you also multiply by the number of moles that appear in the balanced equation. High atom economy reactions are considered desirable because fewer atoms are wasted, which usually means less byproduct to dispose of, and that process is both safer and more sustainable. Low atom economy reactions are undesirable because they generate more waste for the same amount of useful product. So to see how this works in practice, let's walk through the production of phenol. The balanced equation shows that 2 moles of benzoic acid react with 1 mole of oxygen to produce 2 moles of phenol and 2 moles of carbon dioxide. For atom economy, we only count the atoms that end up in the desired product, which in this case is phenol. The carbon dioxide does not count towards the atom economy because it is a byproduct and not part of the target chemical. So when we calculate atom economy, the numerator is the mass of the desired product formed. We have 2 moles of phenol, and each mole has a molecular weight of 94 grams per mole. So the numerator is 2 times 94. The denominator is the total mass of all reactants used. We start with 2 moles of benzoic acid at 122 grams per mole each, plus 1 mole of oxygen at 32 grams per mole. So the denominator is 2 times 122 plus 32. When we divide the mass of useful product by the total mass of reactants and we multiply by 100%, we get an atom economy of 68%. That means that 68% of the atoms we started with are incorporated into phenyl, while the remaining 32% end up in the carbon dioxide waste stream. Now, to end this lecture, we're going to double check our understanding with two final questions that tie together both corrosion prevention and atom economy. The first question asks about the role of magnesium when it's attached to underground pipes. So the statement says the element magnesium is used as a blank for underground pipes by connecting a piece of magnesium metal to the pipe with a wire. This method works because magnesium is blank. So here magnesium is not being used as a coating. It is not sitting on top of the pipe to block oxygen and water. Instead, it's being used as a sacrificial electrode, which means it is intentionally allowed to oxidize so that the iron in the pipe does not. Magnesium is much more active than iron, so it loses electrons more easily. In other words, it's easy to oxidize. So that makes the correct answer, sacrificial electrode, easy to oxidize. Now let's look at the second question, which focuses on atom economy. We are comparing two different reactions that both produce sodium metal, and we want to decide which route is greener based on atom economy alone. Reaction 1 converts sodium chloride into sodium metal and chlorine gas. Reaction 2 converts sodium carbonate and carbon into sodium metal and carbon monoxide gas. First, let me remind you that atom economy is the mass of the desired product formed divided by the total mass of all reactants that go into the reaction, and that is all multiplied by 100%. Only the atoms that end up in the target product count in the numerator. Let's calculate reaction 1. Our desired product is sodium metal. The balanced equation gives 2 moles of sodium atoms. Each mole of sodium has a molar mass of about 23 grams per mole. So the numerator is 2 times 23, which is 46 grams of useful product. The reactants are 2 moles of sodium chloride. Each mole of sodium chloride has a molar mass of 58 grams per mole. So the denominator is 2 times 58, which is 116 grams of reactants. When we divide 46 by 116 and we multiply by 100%, we get about 40%. So reaction 1 has an atom economy of roughly 40%. Now reaction 2, again, the desired product is sodium metal. The balanced equation gives us 2 moles of sodium, so the numerator is still 46 grams. The reactants are 1 mole of sodium carbonate and 2 moles of carbon. 1 mole of sodium carbonate has a molar mass of 106 grams per mole, and each mole of carbon is 12 grams per mole. So the denominator is 106 plus 2 times 12, which is 130 grams of reactants. Dividing 46 by 130 and then multiplying by 100% gives us about 35%. So reaction 2 has an atom economy of roughly 35%. Putting this together, reaction 1 has the higher atom economy, about 40% compared with the 35% for reaction 2. So that means reaction 1 is greener by the atom economy criteria. With that, we've completed this lecture and this unit on redox reactions and electrochemistry. I hope it helps. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.